Can you hear me? Today, why only 24 people, only 23 people? What happened? People are busy today? Are not interested in high voltage class? What happened? No idea. So that means people have all understood or learned high voltage. So no need to come to class. Good, I am happy. Anyway, then let me start the class. Already 6 minutes over. So I will share my screen. You have just tell me. You just tell me whether you can see it. It should come on your screen now. Now you can hear me, students.
Yes, sir. Yes, sir.
Okay, now I will start the class. Now just tell me whether something is coming on your screen. Is it visible?
Yes, sir. It is visible.
Good. So now today I am going to talk about generation of impulse voltage. If you have gone through the notes of the last classes, you have seen that we have discussed about AC and DC generation, but now I am moving on to the impulse. First of all, I have to tell that probably I will, if time permits or if you have some free time, I will take a special class on over voltages in electrical power system. I mean, that's not only just high voltage. I mean, in general, what are the different over voltages that actually every student should know, because this is very, very interesting as well as practically important. We generally subdivide or categorize these over voltages into two groups. One is we call internal over voltages. So what is internal over voltage? Typically, these are the voltages which are generated due to the switching. That means it is internal to the power system. So if there is a switching which is due to so many reasons, typically there may be some power switch on off, or we can switch off a circuit breaker, we can switch off or on a capacitor or an inductor, so many things. So whenever such switching occurs, you all know that that is always associated with a transience. And transience means always some overshoot over the rated or the normal voltage. So we call them internal over voltages. But then there is a big category called external over voltage. Now, external overvoltage means these are the overvoltages which are not generated within the system. These are generated outside the system. Now, what are these voltages? Typically, this is the lightning, the natural lightning. Now, you all know that natural lightning, nobody can do anything, it will happen. But let me just explain one or two very interesting things about lightning. First of all, this lightning stroke that generally happens, that is divided into two categories again. One is called direct stroke, the other is called indirect stroke. So let me explain briefly what are these two. Direct lightning stroke means that the lightning hits the the conductor of the high voltage line directly. Now, if you look at this figure which is on your screen, this is a typical transmission line. It's a double circuit line. So there are 6 conductors. Now, for every transmission tower, on top of the transmission tower, there is always a wire which runs. We called it the ground wire. But this is not used for the earthing of the system. No, this has nothing to do with the earthing of the system. Then what is this? This is used to protect the transmission tower so that the lightning does not hit the transmission line conductors. Now that can be, there are a lot of works on this, so we can show that there is a protective angle. That means if you take the vertical line passing through the tip of the transmission tower, and then we can draw two angular lines with a certain angle 2 theta between them, and it can be shown that within this 2 theta, the lightning will not strike. But then the question is whether lightning will not strike at all. The answer is no, it will strike. Where it will strike? It will strike on the ground wire. Now, when a lightning strikes a ground wire, then another question, hello, if, so this lightning stroke which happens or which occurs on the wire, how do we specify this lightning stroke? That is a very big question. Very big question. Now, we don't specify the lightning stroke by its voltage. We specify the lightning stroke by its current. That means we typically specify the lightning by a certain kiloampere. For example, here it is shown that there is a 100 kiloampere lightning striking the ground wire. Then you can ask me, okay, fine, 100 kiloampere has struck, but then we always talk about the lightning voltage. So how the voltage is coming? Yes. That explanation is that this lightning, when it strikes, then it travels along this conductor as a traveling wave. Hopefully we'll study that also. Now this traveling wave, particularly this current when it travels, then it encounters an impedance which is not R plus JX sort of impedance. Then it is called surge impedance. Now that surge impedance, whatever is Z, then this current multiplied by surge impedance is converted to the equivalent voltage of that lightning strike. Now, if you ask me what is the surge impedance of a transmission tower, it will be approximately around varying between 300 to 500 ohms. The bigger towers will have something around 500 ohms, the smaller towers will have something around 300 ohms. Now, if it is 300 ohms, even if it is 10 kiloampere, which is a very common lightning, then you can see the voltage becomes 300 ohm into 10 kiloampere, which means 3000 kV, which is very, very high voltage. So if that voltage appears, nothing can prevent a flashover. So we have to somehow, uh, ensure that the lightning doesn't strike the conductor. If the lightning strikes the tower, what happens? Then this lightning goes to earth through this tower, and then when the tower is connected to R, that is the base of the tower, there is a definitely a certain resistance is there. It's never zero, right? Any conductor, if it touches the earth, it doesn't resistance doesn't become zero. So this is typically called tower footing resistance. Tower footing resistance. So this will be low. So it is varying between 5 ohm to 10 ohm. So what happens? I'm not going into that. This traveling wave travels towards Earth, but then traveling wave always has a property of reflection and refraction. So there will be a reflection, and effective voltage will be the incident voltage plus the reflected voltage. And it can be mathematically shown that since the tower footing resistance is 5 to 10 ohm, tower surge impedance is about 300 to 500 ohms, so there will be a negative reflected voltage. So the net voltage, the lightning voltage, is much, much reduced because of this negative reflection. And this is one of the reason we try to keep the tower footing resistance as low as possible. That is part of the tower design. Those, if you have in future have the good fortune of working somewhere, then you will see that all these things which apparently looks quite simple, they are not that simple. There are a lot of intricacies involved. So this direct lightning stroke will protect through this ground wire. And if any lightning somehow strikes the conductor, then forget about it. There will be flashover. Nothing can be done about that. But why we don't consider that to be so important? Because the probability is significantly lower when we have this ground wire running on top. But what is so common is the second one. It is called the indirect lightning stroke. This happens multiple times in one single day. Why? Just think about this situation that there is a conductor running, and I'm not considering tower, just simply the conductor running. And there is a cloud here, and the clouds are always charged. You know that. This cloud is hanging over the conductor, say rainy season. Then what will happen? Because of electrostatic induction, which nobody can stop, there will be charges induced on the line conductors. If the cloud is positively charged, then the line conductor will have negative charge. But in most of the cases, cloud is negatively charged, so the line conductor will have positive charge. Now, what these charges will do, you all know that these line conductors have certain capacitance with respect to R. So these capacitances will get charged. But since this cloud is here, so these charges will be bound charges, electrostatically bound. But then there will be wind and all that. So after some time, this cloud will move away. The moment the cloud moves away, these bound charges on the line conductor are no longer bound. They are free to move. So they will then try to move along the conductor and try to flow towards Earth. But then effectively what will happen that there will be a traveling wave. Again, these are all charges. So movement of that is effectively a current. So there is a traveling wave phenomena. And that will give rise to certain over voltages, but that will not be as high as the direct lightning stroke, but definitely of a significantly higher value than the normal voltage. But as I said, that these voltages are, I mean, can happen multiple times in a single day. So primary consideration is always given to protect our equipment against indirect lightning strokes. That means the voltages that are being generated due to indirect lightning stroke. For example, if you go through the Indian standards, there you will find that if it is an 11 kV system, which means the conductors are much closer to Earth, that plays a big role in this sort of induction. The typical voltage that, rather typical withstand voltage is 75 kV peak for impulse, and that comes not from the direct lightning but comes from the indirect lightning stroke. So this is all explained here. But then a very basic question you have to ask me, that we know AC, that it is a sinusoidal waveform. We know DC, it is a constant voltage, but there may be some ripple. But what about the waveform of the impulse? Yes, the answer is very clear, that this has been studied extensively, this waveform, not now, almost 80, 90 years back, and it has been now well established what is the waveform of an impulse voltage. This impulse voltage, first of all, it is called an impulse, and you know what is the definition of impulse, that it's uh, any quantity that is of very high magnitude but duration is very small. That high magnitude, small duration. This is the typical definition. So, this impulse voltage is also of very small duration, but then it's not a constant voltage, neither it is a repetitive voltage, but it is a pulse. That means it is unidirectional. This is first thing we have to remember. So it will have a polarity, either positive or negative. And since it is a pulse, it will have a peak value. So as you can see here, it will have a peak value, it will have polarity, and finally, there will be a wave shape which is typically defined in terms of two times. One we call wave front time, the other is called wave tail time. Now I'll discuss wave front time and tail time, but let me give you the values. As per IS 2071, which is our Indian standard for this, the wave shape of standard lighting impulse voltage is, wave front time is 1.2 microsecond, but there will be always a tolerance on that it will not be exactly 1.2 microseconds, so plus minus 30%. What is this wave front time? That is the time required to go to the peak. What is the then wave tail time? It is 50 microsecond with a tolerance of plus minus 20%. What is the tail time? That it is to come down from the peak value to 50% of the peak value, as you can clearly see in the graph, that this point H is corresponding to 0.5 of the peak value. So wave front time is the time required to reach the peak, and wave tail time is the time required to reach 50% of the peak value when it is decreasing. But then when I say that, you should also ask me a basic question, that fine, you are telling all that, but then what is t is equal to 0? That means what is my reference time? That's a very big question, in fact, because these lightning transients are so random and so fast that this exact t is equal to 0 is very difficult. And by the way, remember, this has to be always measured. And as an engineer, please remember one thing, that if we cannot measure anything, that is of no value. We cannot do anything if it cannot be measured. So we have to measure it with the help of any. Earlier we used to use the cathode ray oscilloscopes, in short CROs. Nowadays we use the analog to digital converters. So whatever it is, you can do that. But then whatever you do, we find that this t is equal to zero. That means the origin is always very difficult to identify. So we have made a separate technique for finding this origin. What is that? It has been noticed that the front part of the wave, that means the increasing part, is mostly linear, that means straight line. It is nonlinear near the peak, it is nonlinear near the zero. Between 30% of the peak value to 90% of the peak value, it is typically a linear curve. So, what is being done is that by applying this very simple geometric rule, we take 2 points B and D, which is point 0.3 and point 0.9 V peak, and then on the x-axis we take A and C, and we find out what is the time difference between this, and then simply by proportion we find out what is the time required to reach the point G, which corresponds to the peak of the F. And then what is the origin? That is also very straightforward. What we do, we take the 2 points B and D and then extend it or extrapolate it, and this straight line where it cuts the x-axis, that is O prime, is our origin. And this is very clearly defined, so there will be no problem. So all this time, that means this 1.2 microsecond, 50 microsecond, everything is measured from what we call the virtual origin, the virtual origin of an impulse wave. There are impulse waves which are caused due to switching impulse. Switching impulses are much slower, not as fast as lightning impulse, because you can see lightning impulse, the front time is as low as 1.2 microsecond. So if you take 1 by t, which gives its equivalent frequency to be of the order of 1 megahertz. But switching impulse, the front time is of 250 microsecond with a tolerance of plus minus 20%. The tail time is 2500 microsecond, tolerance of plus minus 60%. Now this you can read and you can clearly understand. There is nothing so difficult in it. What I will discuss is what is the principle of impulse voltage generation. First you take figure 41 as shown. Don't bother about the figure number. This is taken from another note. So take simple two capacitors in series and consider that capacitor 1 is already charged up to a DC voltage of V, and there is a switch S. What we are doing is we close the switch S. So the capacitor C1 charges the capacitor C2. What happens? The charge balance is such that when C1 is charging C2, so C1 is losing charge, so the voltage of C1 is decreasing. But C2 is gaining charge, so the voltage of C2 is increasing. So at one point of time, the voltage of C1 and C2 becomes equal, and that's the peak value. That is the highest value to which C2 can be charged. And if C1 is equal to C2, then we all know that the voltage that C2 will be charged will be V by 2. Now that is one of the simplest cases. Let us modify it. That figure 42, we have incorporated two resistances here, R1 and R2. When the switch S is closed, now you see that C1 is charging C2 over the resistance R1. So naturally, there will be a certain time lag because of the time constant of the charging circuit. So by controlling this time constant, we can adjust the front time. That means what will be the time required to reach the peak value of the voltage across the capacitor C2. Once C2 is charged to its peak value, then voltage of C1 and C2 is same as I stated earlier. Then what will happen? Then you can see both C1 and C2 has one resistance, that is R2 in parallel. So what will happen? C1 and C2 will start discharging through R2, and the moment start discharging, the voltage of C2 starts decreasing. So when C1 is charging C2, the wave front is generated, and that is over a resistance R1. So that time constant actually determines the wave front time. And after reaching the peak value, both C1 and C2 discharges through R2, and this discharge time constant determines the wave tail time. So it is a quite simple circuit, which in fact, if you are good at simulation, you can even do a very simple simulation and see how this is generated. The big question always comes is about this switch S. Please remember that we are not talking about 1 volt, 20 volt, 100 volt. We are talking about 100 kV, 200 kV. Initially, when the C1 is fully charged, let's say up to 100 kV, and S is open, then the left-hand side of switch S is connected to a 100 kV source, but right-hand side is at 0 volt because C2 is not charged. So this switch has to withstand 100 kV under open condition, and then it has to close the circuit very, very quickly because the lighting impulse itself, the front time is only 1.2 microseconds. So if the switch cannot close the circuit very fast, then you will never get the wave front properly. Therefore, two questions come that how can I get a switch which will be able to withstand that much of high voltage when it is open, and at the same time it can close the circuit at extremely fast or extremely small time. Now, you can always say that why don't you use SCRs? Yes, but practical experience show that it is extremely difficult to have SCRs for this operation because SCR doesn't have a rating of 100 kV. So what we have to do, you have to connect a lot of SCRs in series so that it will be able to withstand 100 kV or 200 kV when it is open condition. But when you have large number of SCRs in series and when the SCRs gets turned on, you all know that there is a turn on time of SCRs, which is well defined by the manufacturers, but still there will be some difference from SCR1 to SCR2 to SCR3, etc. And it is extremely difficult to exactly synchronize the turning on of all the SCRs. So that creates quite a problem and distorts the wave front. So what to do? What is the solution? The solution is actually very, very simple. It has been found long time back that we use a sphere gap. The sphere gap, you have two spheres, in between you have air. So when it is, sphere gap is not having any discharge, it is simply open. And if the breakdown of air occurs, then it is closed. The breakdown of air is a very, very fast affair, and that itself can occur in sub-microsecond time. And there is absolutely no issue of any insulation because a sphere gap, when they are in not flashover or unbroken condition, unbroken means there is no breakdown, there is no issue of any insulation. So this fast acting switch, what we used as this switch S in the circuit is actually a sphere gap. So basic impulse generator circuit, we have two different types of circuit. First of all, what we have is CS. CS is called the stage capacitor, which we charge when the S is open. But for this charging, we need a HVDC source. And this HVDC source could be our HVDC generator, which we have in our lab. So this HVDC source over a charging resistor, by the way, never charge a capacitor without a resistance. Then your source will be damaged. Because a capacitor initially is a short circuit when it is uncharged. So if you connect a voltage source will be directly short circuited. Don't do that as an electrical engineer. So put always a series charging resistance, which you can see here, RCH. When CS is charged, and by the way, one terminal of CS has to be earthed. Never operate a high voltage system without proper earthing. And then these two resistances, the series resistance is called damping resistance. I will explain why. The parallel resistance is called discharge resistance. Discharge resistance is quite clear from earlier discussion that both these capacitors discharge through this resistance. Why the series resistance is called damping resistance, that I will explain. Now, RD can be after RE on the load side or before RE on the source side. Depending on that, the circuit shown in figure A is called the source end connection of RE, because RE is connected on the source end, and circuit B is called the load end connection of the discharge resistance. As you see, RE is connected on the load end. And the capacitor CB, this is not a capacitor of the object which is tested. This is actually a capacitor placed in the generator. This is called the load capacitor. And if you ask me the values, typical values are here given. Normally, this damping resistor RD is about 10% of RE, and the load capacitor is about 10% of the stage capacitor. This actually comes from long experience. Looking at this circuit, if you see, consider that how the initial stage happens when the AC is closed. Now, the stage capacitor CS is initially charged. CB, that is the load capacitor, is uncharged. I am closing the switch S. And then naturally the circuit looks like this. That CS is charging CB over D. Now this is a series circuit, so the equivalent capacitance is as shown on your screen, and the time constant is also like this. And therefore, with this time constant, we can adjust the wavefront time. Of course, it is not that simple to do exactly, because we have neglected RE in this figure 44, but we can always do the Laplace transform calculation and get the exact value. This is equivalent, an equivalent circuit to explain it to you. So this is for charge transfer from CS to CB that generates the wavefront. And then when the charge transfer is all complete, that means voltage across CS and CB are same, then we have this circuit. Both the capacitors are discharging through RE. Now this is a parallel circuit because capacitors are discharging in parallel, and with small approximation we put RD in series with RE, because remember RD is 10% of RE. So this is a valid approximation which brings in small error. So time constant is as shown in the figure, which clearly shows that this time constant is much higher compared to the time constant on the top of your screen. So wavefront time will be much less, wave tail time will be higher, because as per standard, wavefront time is 1.2 microsecond and wave tail time is 50 microsecond. Now, as I said, that we want to do it rigorously, not just by any simple method. So we go for Laplace transform. So on the left, we take the load end connection of the RE. CS is charged to a voltage V0, DC voltage. Now, when S is closed, on the right side, this is the Laplace equivalent circuit. A DC voltage source, you know, is represented by V0 by S. Then CS is represented by 1 by SCS, then RD, and CB is represented by 1 by SCB. So if I find out what is the expression of Vs, that is the voltage across the load capacitor, that is actually our output voltage, and that should be an impulse. So we do V calculation of Vs by simple network theorem application, and I arrive at something like this, that this Vs means, again go to the diagram, it is the voltage across the load capacitor CB. Please do this arithmetic, algebra yourself. So Vs comes like this, and you can find out what are A, B, and C. And in this expression, these are A, B, and C, and K, and they are all related to only the values of R and C. And therefore, everything can be controlled by controlling the values of resistance and the capacitor. And if this Vs, V0 by K into 1 by A square plus AS plus B, you know, we can always represent it as S plus K1 into S plus K2. And then if you take the inverse Laplace transform to go to the time domain, we get an expression like this, where we have two exponential waves, which are actually superimposed, but one is a positive exponential wave, the other is a negative exponential wave. And what are the values of K1 and K2? It is given here. They are related to A and B. What is A and B? That is on your screen. They are all related to RDs, etc., etc. So you can see these are very, very straightforward analysis. So you can do it yourself. And if we try to see graphically what is happening, so there are two exponential waves. Unfortunately, this drawing is not that good. This dotted line is an exponential wave where K1 is small, so the rate of change is relatively less. And it starts from a value V0 by K into 1 by K2 minus K1. That comes from equation, this one, right? This left-hand side. And then another term will be minus of this. That will be this negative wave, but here K2 is much higher, because you can see here K1 is A by 2 minus of this, and K2 is A by 2 plus of this. So K2 is higher than K1. If K2 is higher, then rate of change of the negative wave will be much higher. So what will happen initially when this positive one is decreasing but at a slower rate, the negative one is starting from the same value, one is positive, the one is negative, so summation is 0. So that's the origin of the wave. Then the positive wave is decreasing at a slower rate, negative wave is decreasing at a very fast rate. And if you add them, then you see that it will increase. And the negative wave comes to 0 very quickly, but at that point of time, the positive wave has certain value. So that's the peak value of the wave. And then its negative wave is almost 0. You have only the positive wave, which will follow this equation. This, if you look into many books, they will see that this is represented by what is called a double exponential representation of the impulse wave. And by the way, if you are interested in knowing the value, that what will be the K1 and K2, so I have given it here in this table. What is called the voltage efficiency of an impulse generator? It is very simple, that it is Vp by V0. That means Vp is the peak value of the output impulse wave. That is coming from this graph, that what will be the peak value, that is summation of these two, which is definitely not V0, less than that. So you can find out V0. And these two basic circuits, that means the load end connection and source end connection of RE, they basically differ in terms of this voltage efficiency. What is the maximum stored energy? Of course, that depends on what is the energy at, or what is the voltage up to which the stage capacitor was charged. So if it was V0 max, let's say, so that means from this diagram I will again show. Yeah, here you can see CS is charged up to V0. So whatever be the peak value of that one, if it is V0 max, so it is half CS into V0 max square. This energy primarily determines the size and the cost of a generator. That means if I have to build a generator, then we just don't say the voltage that we want as output. At the same time, we must specify what is the energy rating of that generator, because depending on that, many things will depend. But most importantly, the size and cost of the generator. What is the significance of RD? Well, one is, of course, the determination of the wavefront time. But another important thing is that, see, please remember that this circuit, when we say that CS is transferring the charge to CB, the question is there any inductance in the circuit? Yes, of course, we have not placed any L in the circuit, but remember, whenever there is a wear and current is flowing, there will be some inductance. That is called stray inductance. So that will be in series. So if it is a series RLC circuit, you all know that this will be an oscillatory circuit. But to make this non-oscillatory, this damping resistor value has to be this one, which you can see 2 root over L by C, equal to or greater than this. And where C is this. So this RT has to be chosen in such a way that it should not only control the wavefront time, it should also effectively damp any oscillation that might come during the charging of CB, that means during the wavefront. Then you can ask me that why you are not considering it for the discharge circuit. Well, the answer is again quite simple, that in the discharge circuit, again let me show you here. You can see figure 45. In the discharge circuit, this RD and RE are in series, and this RE is 10 times higher than RD. So effectively, it is such that it is always greater than that critical resistance of a series RLC circuit, which is 2 root over L by C. So in the discharge circuit, there is no problem with damping. The entire problem comes only during the charging, that is figure 44, where only RD is in series. So if RD is not having the required value, then what you will get is you will get superimposed oscillation here on the front time. This will not be looking like this, but there will be superimposed oscillations, and that is not permissible as per the standard. So we don't do that, or that's the significance of RD, and that is why RD is called damping resistor. But as I have discussed in both AC and DC generation, that if our output voltage becomes high, or if it is typically higher than 200 kV, then just using one single stage impulse generator makes it extremely difficult. Why? Because it will increase the physical size of the circuit elements. What is circuit element? That means C, R, and all that. And similarly, we have to have the DC source. That means, say, I want a single stage impulse generator circuit of rating 400 kV. But that will mean I need a high voltage DC source of 400 kV. So that will become a problem if we want very high voltage. Then difficulty in using spark gaps at that high voltage. A sphere gap which operate at 100 kV is quite common, but if you want to operate at 400 kV, a lot of different aspects will come. And finally, the difficulty of suppressing the corona discharges. So because of all that, long time back in 1923, there was a scientist in Germany who was also the family name was Marx. he proposed a multi-stage circuit, and therefore even today all the books refer to that as Marx generator circuit, which you can clearly see is 100-year-old circuit. So this technology is of course not known. People are using it for almost a century now. Now this circuit is actually, uh, I have to explain it to you, that entire multi-stage circuit. And let me see what is there else. The triggering is also marked multi-stage, pulse generation. Correct. Now I'll just explain one more thing today, that is what is called a delay cable. This is a very interesting concept. See, whether you use a cathode ray oscilloscope or you use a analog to digital converter, there is always a question that this has to be fired at the right time, otherwise you can't record the signal. For any such recording, there is always one is called a sweep signal. That sweep signal comes to the what is called the horizontal plate, or for that matter in digital, analog to digital, it's x-axis. And on the y-axis, we have the signal that is being recorded. Now, this sweep signal, if it is not present on the x-axis, then you can't record the y-axis quantity. Now, try to understand that this is shown to be a CRO. This can be also a AD converter in the control room, because these are always in the control room, which is far away from the generator. Because an impulse generator, when it is running at 400 kV, you cannot stay near this for safety reasons. So you have to use cables to bring that signal from the impulse generator to the control room. But then in the control room, when this signal comes, we have to ensure that the x-axis is fired before the y-axis. Why? Because otherwise you can't record, or you will miss some part of the initial part of the y-axis quantity. But if you miss that for a lightning impulse, that is almost half of the wave gone, because the wave front is only 1 microsecond. So if you miss even for 0.5 microsecond, half of the signal is gone. So that's not, that cannot be done simply. So what do we do? So we have to ensure that the signal comes to the y-axis after the sweep signal has started. How do we do it? Typically, we measure this high voltage using a potential divider, because you can understand 400 kV impulse, you cannot feed it to any electronic circuit. So we use a potential divider, reduce the voltage, and that reduced voltage comes through a cable to the y-axis. Then there is the x-axis also. So what do we do? We put up a antenna very near to the impulse generator. So when this sphere gap, which is inside the impulse generator, that is the switch, fires, this antenna catches this signal, because this firing of sphere gap will generate some electromagnetic radiation. And then this signal will come directly to the x-axis and it will fire the x-axis. Fine, but then how do you ensure that the x-axis starts before the y-axis? For that, there is a very well-known knowledge that the propagation velocity of a signal along a transmission line is this, where c is the velocity of light. Now, for any normal signal cable, mu r is 1. So, we can say that the velocity of the signal through a signal cable, which was the signal cable here, this signal cable from potential divider to our recording device, that will be light up speed divided by square root of 4. Now, if you can see, if this epsilon r is 4, so then this is c by 2. So we can clearly see that what is the time required, or rather, we call it transit time per unit length. That will clearly be 1 by v. What is v? V is this one, which is directly related to c and epsilon r. So we can clearly calculate that what is this in microsecond per centimeter. So therefore, if I want to incorporate that a delay of tau has to be incorporated, so this tau therefore will be this t. Capital T is nothing but this transit time. So, and if we use a standard signal cable using solid propylene or Teflon, so propagation velocity is typically 60% to 70% velocity of light. So we can find out that if v is 70% of velocity of light, what is the value of t? So if I want this delay of tau as a microsecond, it will be how much length of the cable is required. So we can simply calculate from this expression. And what we then do is simply we put this cable, which is from the potential divider to the recording device of that length. So if it is 20 meter, then we'll put a 20-meter cable. If it is 15 meter, we put a 15-meter cable. So what will happen? This antenna signal that comes without this sort of signal cable, this comes with a sort of bare cable, because this is a very low voltage. So no insulation issue is there. So it will come almost at the light speed of light, whereas the impulse signal will come through the delay cable, where the speed of signal propagation is only about 60 to 70% of light, and then depending on the length of the cable, we get a certain delay, and therefore we ensure that the x-axis is fired before the y-axis. So this is called a delay cable technology, and you can see here that by incorporating a very simple cable, how we can synchronize the recording operation. This is what is called the ingenious use of technology. So now everything should not be of a very sophistication, but here also you can see there is sophistication, but in a different way. So that is for today. In my next class, I will discuss the multi-stage circuit. So I closed here, and I will naturally send this note to you. Any questions from your side?
No, sir.
Thank you. Uh, by the way, just one question from my side. See, there are a lot of discussions going on about the class and all that. I think you also know. So I'm not very sure how things are going to shape up. Uh, what I suggest is that if things doesn't really shape up well, then at least in the next class also you attend it in this mode, so that we can continue with the class. Otherwise, there will be break in the class. This is something is my view. If there is any other development, of course, you can email me. And if there is a development that maybe